Let's take a look at another example of static equilibrium. A mass of 3 kilograms, here it is, hangs at rest from 3 strings as shown in the figure on the right. Okay, so the first string is here, the second string is here, the third string is here. The tensions and angles for 2 of the strings are labeled on these spring scales. The third string is vertical with an unknown tension. Draw a free body diagram for the hanging mass, and then we're going to work on a couple other problems in part B down here. Okay, so let's start by drawing a free body diagram for the hanging mass. And this really should probably say draw a free body diagram for this point right here. Okay, so that's what I'm going to do. I'm going to highlight that point. It's the intersection of all those strings. First of all, the hanging mass is going to pull down with a force of gravity equal to 3 kilograms times 9.8, which is 29.4 newtons. Okay, the tension in the first string, I'm going to call that T1. I'll call this T2. I'll call this T3. Okay, the tension in the first string is 15 newtons. Let me space that out a little bit more here. Okay, that's from this is like an old school scale. Like if you've ever gone to a grocery store that has a scale for measuring the weight of your bananas, your apples, or whatever, there will oftentimes be like a dial in the middle of it that will point to a number, right? Or the other one, a dial that will point to a number. That's what this picture is trying to show. The tension in the second string is unknown, it said. The tension in the third string is 22 newtons, reading that from here. All right, so the mass supported by 3 strings, we want to know what the tension in that middle string is. Okay, so before we get there, we're being asked to show that the net force in the horizontal direction is 0. We do that this way, summing the forces in the x direction, setting it equal to 0. Okay, so which forces have x components? That's a helpful place to start. Well, looking at the picture, this force is pulling leftward. This force is pulling rightward. So they have horizontal components. T2 is just upwards. That has no horizontal component. And the force of gravity is just downwards. So that has no horizontal components. Okay? So I'm just going to pay attention to T1 and T3. Now, specifically, within T1 and T3, their components will look like this. T1 is pulling upwards and leftwards. Okay, so I'm going to call this T1x. I'll call this T1y. T3 is pulling rightwards. I'll call that T3x. And it's pulling upwards at the same time. I'll call that T3y. Okay, so those are their components. Once I break it into the components, I can actually, kind of ignore this part and just focus on those components. All right, so summing the forces in the x direction looks like this. I'm going to have T3, just the x component, that's pulling to the right, plus the negative of T1x, because it's pulling to the left, and I'm going to set them equal to 0. Okay, well, T3x is going to be related to a 50-degree angle. T1x is going to be related to a 20-degree angle. Okay, so T3x is going to be T3 times the cosine of 50 degrees. And then T1x is going to be the value of T1 times the cosine of 20 degrees. Setting that equal to 0. Well, T3 is 22 newtons times the cosine of 50 plus T1, which is 15 newtons times the cosine of 20, And when I punched it into my calculator and added up, it actually does equal 0. So that checks out. Okay, let's move on to the second part, which says determine the tension in the vertical string. And, specifically, I'll help you out with the numbers here. This gives me 14.1 newtons, and this gives me 14.1 newtons negative. So that does equal 0. A little bit more specific for you. Okay, let's try the tension in the vertical string, part 2. And let's try to clean up some of this mess. All right, if I'm going to determine the tension in the vertical string, I am going to sum the forces in the y direction. Because T2, right, which is my unknown, is a purely vertical force. So I want to sum the forces in the y direction. And I'm going to set it equal to 0 because this object is at rest. So it's in static equilibrium. The net force in the vertical direction will be equal to 0. Okay, so let's come up with an expression for summing the forces in the y direction. First, let's look at my picture. T1 has a vertical component, so I will include T1. T2 is 100% vertical, so I will include T2. T3 has a vertical component, so I will include it as well. And the force of gravity has a vertical component. So I'm going to use all 4 forces when summing them in the vertical direction. And it's going to look like this. I'm going to use T1's y component plus T2 plus T3's y component plus the force of gravity, which is down, so I'm going to make it negative, and I'm going to set it equal to 0. And again, the goal is to try to figure out what this one is. So here we go. T1y is going to be the value of T1, which is 15 newtons. And the vertical component is going to be the sine of that angle, 20 degrees. Okay? T2, I do not have to break it up into its components. It's already 100% vertical. So I'm just going to leave it as is. And it's my unknown. T3, I do have to break up. So I'm going to take the full value of T3, which is 22 newtons, but I'm going to break it up into the vertical component, which is the sine of 50 degrees. Plus force of gravity, setting that whole thing equal to 0. Okay, from that whole expression, I just have one unknown. So I can subtract, pull this over to the right side, pull this over to the right side, pull this over to the right side, and get that T2 equals 7.42 newtons. And that's it. That came from summing the forces in the vertical direction, setting it equal to 0.